Good evening, dear viewers of Akshi.com, by Vetri from Pondicherry. Last class, I have discussed what is thermodynamics, what are the important terms involved in thermodynamics I have discussed. Under this, I have also discussed what is internal energy, change in internal energy, enthalpy and change in enthalpy, and the relation between these two also I have discussed. Today, I am going to concentrate on the laws of thermodynamics. What are the important laws that we must understand under the thermodynamics? Number 1, zeroth law of thermodynamics. Number 2, first law of thermodynamics. 3, second law of thermodynamics. And 4, third law of thermodynamics. So let me go one by one. Slowly, kindly follow me. First, let me take zeroth law of thermodynamics. Very simple, but it's not having so important as per the examination point of view. Anyhow, you must understand. What is zeroth law? If A and B are in thermal equilibrium with C, then A and B are also in thermal equilibrium. Very simple law, zeroth law. Let me repeat again. If A and B are in thermal equilibrium with C, then A and B are also in thermal equilibrium. Let me explain. So here A, it is in thermal equilibrium with C. B, it is also in thermal equilibrium with C. Now, according to this law, now A and B also will be in thermal equilibrium. This is very simple, zeroth law. So, I will not waste time in this. So, let me go for first law. What is first law of thermodynamics? Kindly follow. A number of statements, different statements are given by different persons. I will give all the statements because sometimes any one of the statements they will give in the examinations, and this is the first law, second law, third law they can ask. So you must know what are the statements that are given under the first law of thermodynamics. Number 1, energy can neither be created nor destroyed, but can only be redistributed. Very most important, because this is nothing but law of conservation of energy. In the beginning of the last class, I have discussed this. So, we cannot create energy, we cannot destroy energy. What we can do if at all? We can convert from one form to another form, or can only be redistributed. This is the most important statement of first law. Then, second statement. The total energy of an isolated system is constant. This is again another interesting statement. First law statement. What is the isolated system? I have already explained last class. An isolated system is one from which neither mass nor energy will be transferred to the surroundings or surrounding to system. This is called isolated system. So in an isolated system, so there will be no absorption of energy, there is no release of energy, so that the total energy of an isolated system is constant. This is very interesting information. Okay. Third one. The total sum of the mass and energy in the universe is constant. This is also the third statement of first law. The total sum of mass and the energy in the universe is constant. What is universe? I have already explained. A system and its surroundings are called universe. So in the universe, so total mass and total energy will be always constant. This is another interesting statement of first law. Okay, let me go further. Next statement. This is another interesting statement. Heat and work are equivalent ways of changing a system's internal energy. Very interesting statement of first law. Heat and work are two equivalent methods. We can change the internal energy of any system. Kindly follow. Heat means heat can be absorbed, heat can be released. Work means work can be done by a system, work is done on the system. By both ways, depending upon the nature, now a system can change its internal energy. This is the very, very interesting statement. Next statement, fifth one. Whenever different forms of energies are converted into heat or vice versa, there is a fixed ratio between quantities of energy and heat thus converted. This is the most important, again, another statement. So these are the ways we can define the first law of thermodynamics. Okay, now this is just now I have given the different ways the different author given as the statement for first law of thermodynamics. So let me concentrate next. The further important three important information under the first law of thermodynamics. One is, I will derive mathematical form. How to represent the first law of thermodynamics? Mathematical form, I will concentrate. Second thing, what is the drawbacks of first law? And also, under this, I can also discuss his law of constant heat summation. Or another interesting heading will be normally given all books, is called thermochemistry. It is called thermochemistry. This law of constant heat summation is also known as thermochemistry. If you go for B.Sc level chemistry book, they will be given separately as thermochemistry. Okay, let me concentrate one by one. First, let me discuss mathematical forms of first law. Mathematical forms. Kindly follow, just before entering into the mathematical forms, just kindly follow me. So, if you see your CBSE book, and when they were discussing about the first law of thermodynamics, and what they are giving is, they are giving this form, that is U2 minus U1, that is delta U equal to Q plus W. They are giving this is the first law of thermodynamics, they say. But if you go for a Samachir book, and they are giving another form, that is delta U equal to Q minus W. So when students have come across the books, CBSE as well as Samachir, they will be getting confused. So I will explain. Need not confuse. So the author having in the information specification, they are giving that. So I can give you a clear idea, kindly follow me. Now, so in order to give you a mathematical form for first law of thermodynamics, so I am classifying two ways. One is, first, what will happen during absorption of energy? What will happen during the release of energy? So I divide into two. Then you can go interior. Kindly follow. So let me first take during absorption of energy, what will happen? Absorption of energy means automatically Q will be absorbed by the system. By a system. Q will be absorbed by a system. So internal energy will change its energy. Energy will be increasing by absorption of energy. So Q will be always positive in this case. The first case, during absorption of energy. The second case, during release of energy, Q will be always negative. This is the interesting information. And during absorption of energy, again I am going to discuss by two ways. After absorption of energy, whether work is done by a system or work is done on the system. All these things I have already explained under the work convention. I have already given. So work is done by a system, W will be negative. Kindly follow. Work is done by a system, W will be negative. Work is done on the system, work will be positive. This is the interesting information. So when we are reading any mathematical form of first law, the sign convention you must have it, keep it in mind. If you keep it, give concentration of the sign convention, you will not be getting confused. Okay, let me go concentrate on it. Suppose during absorption of energy, so first case number one, what will happen here? In this case, work done by the system, that is W will be negative. Work done by the system. A specific example, expansion of a gas in a cylinder. So that is expansion, work done by a system. Okay, kindly follow me. So let me start now. A system having an initial energy that is U1. It is having initial energy. Okay. Now what will happen now? We are supplying energy to the system absorbing this energy. So by the absorption Q will be plus, so plus Q. After absorption of energy, work is done by the system, so minus W. Can you follow? So initial energy U1, it absorbs energy, so plus Q. Work is done by the system, so minus W. So after absorption, it is doing some work. So what is the remaining energy, internal energy, that is the final state is U2. So this is the idea you must have. So from this point I can now, I will rearrange, because my aim is I have to get what is delta U. So U2 on the right hand side, U1 on the left hand side. What I will do now, U1 bring on the other form, that is U2 minus U1, that is equal to, kindly follow, that is Q minus W. So this is the one form of, mathematical form of first law of thermodynamics. Kindly follow. So the condition here it is, absorption of heat and work done by the system, so Q minus W. This is one mathematical form. So delta U equal to Q minus W. Again, second case, during again absorption of energy, but work is done on the system. In that case, initial energy U1, internal energy of the system is having initially U1. Heat absorbed by the system is plus Q, absorption always plus Q, and work is done on the system, so it is plus W. So what will be now? So after absorption of energy, work is done on the system, so internal energy changes to U2. Then again, as usual, I will now rearrange U2 minus U1. I will bring U1 on the right hand side. U2 minus U1, nothing but delta U, that is equal to Q plus W. This is the second mathematical form. So kindly listen, students. So during absorption of energy, I can now give two mathematical forms depending upon the nature of the work. If work is done by a system, I can write this equation. Work is done on the system, I can write this equation. So in CBSE, this form is followed. In semester book, this form is followed. So both are correct. So you must have, keep it in mind, that is the interesting information. Okay. The another form, two more forms also, which are not common, but anyhow you must know. So during release of energy, suppose if system is losing energy, how can you correlate the mathematical first form? Let me now say, U1 is the initial energy. A system is having initial energy. So release of energy minus Q. So after release of energy, the work is done by the system minus W. As usual, I will rearrange. That is U2 minus U1 equal to minus Q minus W. This is the third form. So delta U is equal to minus Q minus W, the third form. That is, the energy is released, work is done by the system. In that condition, this is the mathematical form. And the final form, fourth form, as usual, initial energy is U1. Again, the energy is released, so minus Q. Work is done on the system. Work is done on the system, so plus W. So automatically, U2 minus U1, that is delta U, that is equal to minus Q plus W. That is the fourth mathematical form. Can you follow? So these are the ways I can give the mathematical forms of first law. So kindly follow. Normally either Q plus W will be given or Q minus W will be given, but depending upon the problems, given data, you can substitute this equation. Then you will not get any problem. Okay. So after that, let me go for the drawbacks, the limitations of first law. So we have studied statement, we have derived the mathematical forms. Okay. What are the limitations? There are three important limitations. One is feasibility. The first law of thermodynamics fails to explain the feasibility. Again, it fails to explain the direction. And third, it fails to explain conditions. So let me explain one by one. First drawback, feasibility. The first law of the thermodynamics fails to explain whether a change or a reaction will take place or not. Suppose I want to do a chemical reaction, say for example nitrobenzene. I want to further nitrate to metal dinitrobenzene using concentrated nitric acid. Whether the product will form or not, I want to decide. Whether the first law will help or not. So it is not giving any help. Whether the process will proceed or not, it is not giving any information. So for any chemical reaction, first law fails to explain whether the particular process will take place or not. It is not giving any information. It is drawbacks. The second important limitation is direction. At what direction a system will change its process. That is, it changes its state. It's not giving information. That means whether it's a spontaneous process or non-spontaneous process. Whether it's moving towards forward direction or backward direction. So it is not giving any information. So first law of thermodynamics fails to explain the direction in which the change will take place. The reaction will take place. And the most important, the first law of thermodynamics again fails to explain at what condition the change will take place or reaction will take place. Say at isothermal, at constant temperature, or at constant pressure, or at constant volume. At what condition the process will take place? Again, first law of thermodynamics fails. Okay, let me go for the next one. The third important thing is, I have already Hayes law. I have already pointed out this is nothing but thermochemistry. So this is the most important. Most of the problem in thermodynamics are coming asked from this particular subunit. So kindly students, concentrate on this. Let me now go for Hayes law. What is Hayes law? States that the enthalpy change, that is delta H, the enthalpy change of a reaction either at constant pressure or at constant volume is the same whether the reaction takes place in a single step or multi steps, provided the initial and the final steps of the reaction are same. This is the most important statement of Hayes law. Let me repeat again. Hayes law states that the enthalpy change of a reaction either at constant pressure or constant volume is the same whether the reaction takes place in a single step or multi steps, more than one steps, provided the initial and final steps of the reaction are same. So let me explain this law with a suitable example you can understand. But here I have not explained this law, I have given a specific example of formation of carbon dioxide I have given. So carbon dioxide can be formed by two ways. In a single step, first one is a single step process. So 1 mole of carbon graphite reacts with 1 mole of oxygen gas to produce 1 mole of carbon dioxide gas. So delta H, change in enthalpy, it is experimentally determined as minus 394 kilojoule. This is first method, method 1. Okay, the same, the Hayes law, I can now try with the other method. There are two steps. Same process, I can do it in two different methods, two multiple methods. That is, one is, so first is 1 mole of graphite reacts with half mole of O2 gas to produce 1 mole of carbon monoxide gas. So this is the first step. In this delta H1, it is indicated by delta H1. Formation of carbon monoxide is the first step. So the delta H1 value, the value is minus 110.5 kilojoules. Right. The second step, this carbon monoxide gas reacts further with half a mole of O2 gas to produce 1 mole of carbon dioxide gas. The change in enthalpy in this case is indicated by delta H2. The value is determined as minus 283.5 kilojoules. So what is the importance of the law? The first method, only single step, the value 394 kilojoule. The second step, that is second method, it is consists of two steps. But if you add these two, both values, that is delta H is equal to delta H1 plus delta H2, again same value. So whether the reaction takes place at constant volume or constant pressure, or more than single step or more than one step, so the identical pressure. Here it is taking place at constant pressure. This is the Hayes law. Kindly follow. So based on this idea, I am going to explain all the normal reactions that are taking place in a chemical reaction in the laboratory. What are the important changes that you are normally measuring the enthalpy change or heat of a reaction? Number one, enthalpy change of formation, we have to give concentration. Enthalpy change of solution, enthalpy change of dilution, enthalpy change of fusion, enthalpy change of vaporization, enthalpy change of sublimation, enthalpy change of combustion, and finally enthalpy change of neutralization. Or sometimes we can also use heat of change of formation, heat of formation, heat of solution, heat of dilution, heat of fusion also we can use. Always that is represented by delta H. This is the interesting information. Enthalpy change is indicated by delta H value. It may be positive, it may be negative. We have already discussed. Negative means the exothermic, positive means endothermic. But among these, even though I am going to discuss, but in our CBSE as well as our semester book, only the last two given concentration, that is enthalpy change of combustion and enthalpy change of neutralization were given important. Anyhow, I will discuss. Let me go one by one, kindly follow me. Enthalpy change of formation. What is enthalpy? That is delta H. Normally, F for formation. Enthalpy change of formation of a compound is defined as the enthalpy change which accompanies the formation of 1 mole of a compound. Kindly follow. The enthalpy change which accompanies the formation of 1 mole of a compound from its elements in their naturally occurring physical states. Naturally occurring physical states. The specific example here I have given, heat of formation of ethylene, that is the ethylene, heat of formation of methane. So first case, 2 mole of carbon graphite reacts with 2 moles of hydrogen gas to produce 1 mole of ethylene gas, the delta H value plus 52 kilojoules. The second case, formation of 1 mole of methane, it is obtained from 1 mole of graphite, 2 moles of H3 gas, the delta H value it is minus 73 kilojoules. This is the heat of formation. Kindly follow. Let me go for the next one. Heat of change of formation continuation. The enthalpy change of pure elements. So these are the points you must have regarding for having in mind the case of formation, heat of formation. The enthalpy change of pure elements in their naturally occurring physical state are taken as 0. This is the interesting point you must. For pure element, delta H value will be 0. Because when we are doing calculations, this you have to keep it in mind. The next one. The enthalpy change of formation of a compound at atmospheric pressure and at 298 Kelvin is called standard enthalpy change of formation, usually indicated by delta H of dot or 0. That is standard enthalpy change. This is another interesting information. So you should be very careful. Simply when you write delta H, F, heat of formation. But if you write delta H, F and dot, it is the standard enthalpy change. So the two difference you must know. Another interesting information regarding this heat of formation. Right. Generally, a compound which has large negative enthalpy change of formation is more stable. This is the very, very interesting information. So whatever compound is having more negative value, that will be more stable. We have seen already ethylene and methane. Methane is having a more negative value, it is more stable. That is the interesting information. So let me generalize. In all heat of formation of reactions, in general, the enthalpy change of any reaction is equal to, that is total delta H value. It may be exothermic or endothermic. That is the sum of sigma NP delta H of products minus delta sigma, the sum of, that is sigma NR delta H of reactants. That means the total enthalpy changes of products, all the products, minus total enthalpy changes of all the reactants. That will give the total enthalpy change of any chemical reaction formation. This is the very, very interesting information. So when we are doing problem, this equation you must keep it in your mind. Okay, with this idea, now let me go for the next is enthalpy change of solution. These are all simply interesting points. Let me go fastly. the enthalpy change of solution. Solution means we can dissolve solid in a solvent. So during dissolving a solid into solvent, what is the energy change? That we can measure. So that enthalpy change of solid is defined as enthalpy change when 1 mole of solute is dissolved in a definite quantity, n moles of solvent, to get a solution of Hb concentration. So when we have n moles of solvent, then add, that is 1 mole of solute into that, whatever change in internal energy, that is enthalpy change. That is the, at constant pressure we call it enthalpy change. So that we will call it as enthalpy change of solution. Very, very interesting information. The same way, enthalpy change of solution. Once we prepare a solution, then we can change the concentration of one solution to another solution. When we are changing, the delta change also can be measured. That is called the enthalpy change of dilution. Let me explain here. That is, the enthalpy change of a dilution is defined as the enthalpy change that occurs when a solution containing 1 mole of solute, a solution containing 1 mole of solute is diluted from one concentration to another concentration. So once we are preparing, we know heat of solution. After preparing solution, then we can change one concentration to another concentration. That is called enthalpy change of dilution. Specific example. Here I have given. So I have dissolved 1 mole of solenoated in 100 moles of water. I am getting a solution, a particular concentration. So this concentration, if I want to convert into 1 mole in 500 moles of water, so I am adding 400 moles of water. This is called dilution, enthalpy change of dilution. So when I add water, 400 moles of water, so whatever change in enthalpy I can measure, that is called enthalpy change of dilution. Specifically, in the case of silver nitrate, experimentally the value is determined. So when you dilute the 1 mole of silver nitrate in 100 mole of water is converted into 500 moles of water. So that the delta is measured as 1.1 kilojoule. So when it is diluted by adding 400 moles of water, the delta H value is 1.1. This is called enthalpy change of dilution. The next one, same way, enthalpy change of fusion. What is the enthalpy change of fusion? Enthalpy change of fusion is defined as the quantity of heat required to change 1 mole of solid completely into liquid at its melting point. That is called fusion. Solid can be converted into liquid. Whenever solid is converted into liquid, whatever energy required, that change will call it enthalpy change of fusion. So specific example here I have given, 1 mole of solid ice converted to 1 mole of liquid water. So what is that delta is measured experimental value? It is delta H of is equal to 6.02 kilojoule. In the case of enthalpy change of fusion of solid ice. Very, very interesting information. Sometimes question can be asked, if you have this value, you have to memorize. The same way, enthalpy change of vaporization. First case, solid to liquid fusion. Liquid to vapor is called vaporization. So what is enthalpy of change of vaporization? Enthalpy change of vaporization is defined as the quantity of heat required to change 1 mole of a liquid into its vapor at its boiling point. This is called enthalpy change of vaporization. Can you follow? Specific example. Again I am taking water, liquid water, 1 mole. I am converting 1 mole of liquid water into 1 mole of gaseous vapor form, water vapor. So what is the delta change? It is measured experimentally. Delta H of here, it is equal to 40.50 kilojoule. This is the enthalpy change of vaporization. Okay, let me go for the next one. Enthalpy change of sublimation. What is sublimation? We know already. It's a process by which when solid, any volatile solid is heated, it will be converted into liquid, converted into vapor without melting into liquid. This is called sublimation. So, what is the enthalpy change of sublimation? Let me define now. Enthalpy of change sublimation is defined as the amount of heat required to change 1 mole of solid, volatile solid, into vapor completely without melting into liquid at a constant temperature. Is called enthalpy change of sublimation. So enthalpy change of sublimation is defined as the amount of heat required to change 1 mole of solid into vapor completely without melting into liquid at a constant temperature. Specific example, iodine. Take 1 mole of solid iodine, and just if you heat, what will happen? It will not melt into liquid iodine. It will directly go to vapor form. Iodine will be vaporized. That value it is measured experimentally. That value it is delta H sublimation, that is 62.3 kilojoule. Heat of vaporization of iodine. That is, sorry, heat of enthalpy change of sublimation of iodine is 62.3 kilojoules. This is another interesting information. Enthalpy change. Now, the next is enthalpy change of combustion. Kindly follow. This is the, I have already explained to you, indicated in the beginning of the class itself. That is enthalpy of combustion and utilization. We have to concentrate as per your higher secondary level syllabus is considered. Okay, let me concentrate, let me go slow. Enthalpy change of combustion is defined as the enthalpy change which accompanies the complete combustion of 1 mole of substance. Complete combustion of 1 mole of substance in presence of excess of oxygen. Very, very interesting. So you can burn any substance, 1 mole, and completely in presence of oxygen, burn it, whatever the change in enthalpy, you will call it delta H. That is the enthalpy change of combustion. A specific example here I have given, formation of carbon dioxide or heat of combustion of carbon. So 1 mole of carbon graphite form is burned in excess of oxygen O2, 1 mole, giving 1 mole of carbon dioxide. The delta H value is minus 394 kilojoules. We have already discussed under the S law. Okay. Now what are the other important information under the heat of combustion you must know? All combustion reactions are exothermic in nature. This is one important point you must keep it in mind. All combustion reactions are exothermic in nature. The next one. These reactions are used normally in industry, rocket and chemistry. Okay, let me go forward. Further information. What you are now seeing is that the apparatus used for measure the enthalpy change of combustion. That is called bomb calorimeter. Can you follow? That is inside. What we are saying, it is the bomb. Can you follow? The entire vessel, we'll call it as bomb. It is placed inside a wooden box. And we have a thermometer here and stirrer here. And inside a platinum wire is connected, and there is again a platinum cup also inside there. And outside it is covered by water. This is the apparatus, the bomb calorimeter apparatus. Okay, let me, so what, by using this instrument, bomb calorimeter, we can measure the enthalpy change of combustion, basically. So what is the way? Kindly follow. In a typical bomb calorimeter, just now I have shown you, a known quantity, a wide sample of benzoic acid, as normally we can take, say W2, is placed in the bomb, which is placed in the calorimeter, the corresponding, which is filled with excess oxygen and is sealed. Then it is ignited. Ignition is brought into electrically, that is brought out electrically. So allowed to burn in excess oxygen. What will happen now? The rise in temperature is noted as delta T. The temperature rise can be noted with the help of thermometer there. We can note. So we are using a known quantity of substance of benzoic acid and we are noting the delta T. So there is a very interesting equation is there to determine the enthalpy change of combustion. That is, what is delta H? Delta HC, that is benzoic acid, into W2 by M2. That is W2 weight of the benzoic acid used, M2 the molecular weight of benzoic acid. That is equal to WC into delta T. WC, what is WC? This is a specific. That is the value, calorimeter value, that I am going to give the value. Delta T is the different change in temperature. So this value, it was measured experimentally as standard value is given. So it is available in the literature minus, that is 3227 kilojoule per mole. 3227 kilojoule per mole. It is the standard value. So it is a constant value. It is always there. It is a constant value. So using this standard value of benzoic acid, we can determine enthalpy change of any reaction, any combustion of any compound we can determine. So let me explain this. Kindly follow. what way? So I have already pointed out in the equation WC nothing but a water equivalent of calorimeter. It is a value is known from the standard value of enthalpy of combustion of benzoic acid from this equation. So I have already given the equation. Kindly see, this is the equation. So from this equation, WC can be calculated because this value, it is the standard value. Delta T we can measure in the laboratory. So WC we can calculate. So this is the value, constant value. So that's called a water equivalent of calorimeter, WC. So we can calculate. So if you know that value, so knowing the value of WC, use the same equation but check the substance now. The enthalpy change of combustion of any substance using the same bomb calorimeter can be determined adopting similar procedure using the substance in place of benzoic acid. In place of, instead of benzoic acid, we can change any substance you want to identify enthalpy change of combustion, you can substitute. But WC we have already determined from the standard value of benzoic acid, substitute that value we can calculate now delta H of any substance. So by this, using this experiment, the enthalpy change of combustion at constant volume, kindly follow, constant volume is known as that is delta H0 standard, that is V indicates it's the measured at a constant volume for benzoic acid. So WC into delta T. So this value on left side value we have already seen minus 3227 kilojoule. It is known. So delta T we can measure. So what is the WC can be easily calculated. Now the enthalpy, this is for your delta, the corresponding delta H value at a constant volume. But this value we can convert into delta H value but a constant pressure. What we use in the equation? Now the enthalpy change of combustion at constant pressure can be calculated as follows. That is delta H there is at constant pressure is equal to delta H3 at constant volume that we can get from here. Then plus delta N RT. Delta N, the total number of moles of products minus reactants value that you can get from the stoichiometry. Then introduce R value, universal gas transfer value, and the temperature. You can calculate the enthalpy, the change of combustion of any substance at constant pressure. We can calculate. So this is the way we have to determine enthalpy change of combustion. This is the very, very interesting information. Kindly follow. Next, let me go for the enthalpy change of neutralization. Another interesting information you must know. Neutralization. Now what is that? The enthalpy change of neutralization is defined as the enthalpy change which accompanies the complete neutralization of 1 gram equivalent of an acid by a base. 1 gram equivalent of an acid by 1 gram equivalent of a base. Say 1 N acid, 1 N base, 0.1 N, 0. Like that. So here in this case 1 gram equivalent of an acid by a base, 1 N. This is the interesting information. So the enthalpy change of neutralization defined as the enthalpy change which accompany the complete neutralization of 1 gram equivalent of an acid, 1 normality 1 by a base, again base normality 1. So whatever change in enthalpy, we will call it as enthalpy change of neutralization. It is found that the enthalpy change of neutralization of a strong acid and a strong base is always constant. So whenever you neutralize any strong acid with any strong base, it is always a constant value. That value it is minus 57.32 kilojoule. Kindly follow. Strong acid means it may be HCl, it may be nitric acid, it may be sulfuric acid, anything I can use strong acid. Same base means I can use sodium hydroxide, I can use potassium hydroxide. Whatever the difference, whatever acid or whatever base, the value it is same. That is minus 57.32 kilojoule if it is by both strong acid and strong base. This is the very interesting information you must know. Let me explain now. So strong acid and strong base exist in the full ionized form because we are going to study in future. Based on Arrhenius theory, all strong electrons will undergo full ionization. So sodium hydroxide strong base I can write in the form of sodium plus and OH minus. HCl I can write in the form of H plus and Cl minus and complete ionization. So what will happen now? The right hand side, automatically sodium chloride and water is formed. Sodium chloride again a strong electron, completely ionized. So sodium plus cancel, Cl minus Cl. So it is actually Whenever any strong acid reacts with a strong base, the actual reaction is between OH minus and OH plus. That's why it is forming water. That's why the value it is constant. That's why the value it is minus 57.3. That is the value is constant. This is the interesting information. So whatever nature of acid, whatever nature of base, the reaction is always taking place between H plus and OH minus to form water. That's why the value it is constant. That is, we can write another way also. That is, we'll add, that is dissolving this 1 mole of water. So sodium plus OH minus. In this case, I am indicating here as HCl water means, so that H plus of Cl, the HCl, it is combining with the water to form H3 plus, again the same equation, but the only thing in this case, right side, instead of 1 water molecule, 2 water molecules, that's the only difference. Thus, H plus ion produced in water by ion molecule exists as H3 plus. This is the interesting information, kindly follow. Okay, let me go for the next. So far what I have discussed, complete release of strong acid and strong base. Now in case of neutralization of weak acid by a strong base or a weak base by a strong acid, 2 steps are involved. That is, now let me take a specific weak acid by a strong base. What will happen now? Weak acid, acetic acid, that is by a strong base, again sodium hydroxide. So we are normally dissolving in water. So what will happen? The first step, acetic acid dissolve in water to give acetate ion and H3O plus aqueous. The second step, sodium hydroxide giving sodium plus and OH minus, now reacts with correspondingly sodium plus and the OH minus is reacting. So producing now sodium plus and 2S2O. So this is the actual reaction that is taking place in the case of neutralization of weak acid by a strong base. So this is the interesting information. The same way, neutralization of a weak base by a strong acid, again we can now visualize this way. So again ammonium hydroxide water gives ammonium ion, water and OH minus. First step. In the second step, what will happen now? This water, that is again water, this OH minus, that reacts with the again strong acid HCl to produce Cl minus and 2H2O. So this is the interesting information. So now, since the enthalpy change of ionization of the corresponding weak acid or weak base is endothermic, the ionization of weak acid or weak base is always endothermic, that is plus value. The enthalpy of this neutralization is always lower than the neutralization of strong base by strong acid. Very, very interesting information you must have it in mind. I have already pointed out the neutralization of strong acid, strong base will be always constant because it is the reaction between H plus and OH minus. The value is minus 57.32, we have seen already. But if it is a neutralization of a weak acid, strong base or weak base, strong acid, now the enthalpy of neutralization will be always lower than minus 57.32 kilojoule. This is the interesting information you must know. Because additional to there is undergoing ionization of weak acid or weak base, it's always a positive value. So positive will be substituted for negative, so lower value. Right. Now this is the interesting information regarding for thermochemistry, that a difference, the enthalpy change of reaction I have discussed. Even though I have given so many enthalpy change of reactions, I have concentrated. One is the enthalpy change of combustion and enthalpy change of neutralization I have given concentration. Okay, let me go for the next second law of thermodynamics. What is second law of thermodynamics? Kindly follow me. This is statement again. All spontaneous processes are thermodynamically irreversible. Kindly follow. This is the most important statement of second law. All spontaneous process. What is spontaneous? Any process which is taking place without any external agency. It is taking place automatically, without any help, without help of any agency. It will take in automatically. Raining, the specific example. All spontaneous processes are thermodynamically irreversible. Okay. Next statement, another form of statement, second law. A process accompanied by increase in entropy. A process accompanied by increase in entropy tends to be spontaneous. Whenever entropy increases, that will be automatically spontaneous. Kindly have it in mind. The first law fails to explain whether the process is spontaneous or non-spontaneous, but second law helps whether to be, so that means whether to decide if it is spontaneous or non-spontaneous, there is provision is given. If you are able to measure entropy, we can decide just spontaneous or not, because it is given. If entropy the changes, increases, it will be a spontaneous. Then next you can raise the question, what is entropy? I am going to discuss later, but at the time being you can have to me. Entropy is a measure of disorder of a system. Kindly follow. Let me repeat again. Entropy is a measure of disorder of a system. So solid, let me take a specific example, any compound or any element you take. The crystalline arrangement, atoms or ions will be regularly orderly arranged. But if you convert by melting, if the solid becomes liquid, the order will be getting disorder. I can now say the entropy is getting increasing. When a solid is melting into liquid, entropy increases. When a liquid gets vaporized, further the entropy increases. Whenever disorder increases, entropy increases. So kindly have this idea. Let me present now. The other statement given by Clausius statement. Kindly follow. This again, second law of thermodynamics. Entropy of a system, that is disorder of a system, increases by absorption of heat. By absorption of heat, entropy always increases and decreases by evolution of heat. By release of energy, now entropy decreases. This is a very interesting statement given by Clausius. Then next statement. Black statement. This actually chemistry point of view is not interesting. Anyhow, this is the physical point of view is more important. It is impossible to construct a machine which will work in a complete cycle and convert heat into work without producing any change in the surrounding. Let me repeat again. According to Planck statement, sometimes they will ask what is Planck statement? Second law of thermodynamics. Planck statement states that it is impossible to construct a machine which will work in a complete cycle and convert heat into work without producing any change in the surrounding. This is the corresponding Planck statement, the last one. So that is the fifth one. Another the statement of second law. Without use of an external agency, heat cannot by itself pass from colder to hotter body. That means we are having two bodies. One is cold at the lower temperature, another at higher temperature. So heat cannot move from colder to hotter body. This is another interesting statement given by, that is the second law of thermodynamics. Right, the last one again. The efficiency of a machine can never be 100%. Any machine if you take, it will not be 100% efficient. Kindly follow. This again, second law of thermodynamics. Different forms of statement. Right. Now let me explain what is the second law of thermodynamics in first. The essence of second law of thermodynamics, let me explain. Kindly follow. All the spontaneous processes are irreversible. Kindly understand that. So you can raise a question. What is, because I have already given, whenever all spontaneous, whenever entropy change increases, it moves towards the spontaneous. What is spontaneous? You must understand first. What is spontaneous? Let me give you 2 or 3 examples to explain spontaneous process. A cup, one specific example. A cup of hot tea placed on the table. Take a cup of hot tea. And approximately we will say, let us assume we know the mass, we know the energy, the corresponding temperature, and place on the table. After some times, you do not put a fan, you do not cool it, anything, nothing you can do. But after some time, you can see that temperature of the hot tea will slowly coming down. That it is going, the energy, the form of heat, will be transferred from this to the surrounding atmosphere. So cup of tea is the open system. From this energy is transferred to the surrounding. That is the idea. So the cooling of tea taking place automatically. It is a spontaneous process. It is an irreversible process. Kindly follow. It is spontaneous. So this is a spontaneous. Another example. We take a beaker, a drop of ink placed in a beaker containing water. You take a beaker and add a little water, 100 ml of water, add just a drop of blue ink. Just see after some time, the drop will slowly spread into the entire beaker. This is again an example of spontaneous process. The third one. You take 2 different gases, that is 2 different gases, let me say carbon dioxide, like that. another gas methane. Two different gases, but same identical pressure, and then connect by a stopcock. Suppose let's assume now we have here one gas, here another gas. So gas 1, this is gas 2. Let us assume. But both gases are having same identical pressure. Pressure is same. Let me say 10 atmosphere, whatever it is. Same identical pressure. And if you just connect by a stopcock, the gases automatically mixing. This is interesting. Two gases have identical pressure connected by a stopcock will be automatically mixing. This is a spontaneous process. Mixing of two gases automatically taking place. We did not give any pressure, we did not give any external agents required. Another interesting, fourth one. Mixing of equal volumes of same concentration of HCl and sodium hydroxide towards neutralization. So mixing of a strong acid, strong base of same concentration, always neutralization taking place, it is a spontaneous process. We did not heat, nothing we can do. This is the examples of spontaneous process. Now under this, now I have already explained what is entropy and entropy thing. Let me concentrate, kindly understand. If you understand this entropy check, then you can look at it, clearly understand the second law of thermodynamics. Entropy is defined as the measure of the disorder of the system. I have already pointed out, measure of the disorder of system usually indicated by S. Now, entropy of a system increases by absorption of heat and decreases by evolution of heat. We have already given the statement. Second law. So, entropy is a disorder, and by absorption of the heat, the entropy increases. That is, the decreases by evolution of heat. Okay. Now, another interesting. In all naturally occurring process, all spontaneous process, the entropy of the universe increases. Can you follow? This is the idea you must have. The entropy of the universe increases in all natural occurring process, all spontaneous process. But in a reversible process, the entropy of the universe remains constant. It will not change. So in a reversible process, the entropy of the universe remains constant. Okay, the idea here. Next. When a system undergoes a small change of state, small change, microscopic change, reversibly, the change in entropy of the system is equal to the heat absorbed by the system divided by the absolute temperature. So I am giving a definition for entropy change for a microscopic property. So mathematically, ds is equal to dq reversible by t. So ds, change in entropy, dq, that is the heat absorbed by the reversibly small quantity, and t, temperature. So here ds is the entropy change of the system, which is given by a symbol ds S2 minus S1. S1 entropy of initial state, S2 entropy of the final state. This is the interesting information. Next one. Delta S, for a macroscopic property measure, so delta S can be used instead of ds. Delta S can be used to determine the spontaneity of a macro process. Mainly follow. For a macro process, the delta S can be used to determine the spontaneity of macro process. Okay. In an isolated system, we have already seen what is isolated system. For a spontaneous process, the change in entropy is always positive. Now, second law gives very clear idea. For all spontaneous process, the change in entropy is positive. So if we are able to measure change in entropy, we can decide whether a particular process is possible or not. We can decide. So first law fails, second law helps to predict whether the process is taking place or not. It's giving answer. Right. Now, another problem is there under this, because this is for an isolated system. Okay. For open system, we have to consider entropy change of the system and surroundings. If you want to calculate for an open system the entropy of total, so we have to consider entropy change of the system and surroundings to determine the total entropy change. What is the mathematical form? So delta S total is equal to delta S system and delta S surrounding. But the problem here it is delta S of system can be measurable, but delta S surrounding we cannot measure. So that is the problem we are facing. So only if you know delta S, we can determine whether it is spontaneous or non-spontaneous. Kindly follow. So if the total entropy change is positive, the process is feasible. I already pointed out. It is spontaneous. It is possible for, we'll predict now the reaction is possible, feasible. But I already pointed out, it is not convenient to measure entropy change of system and surroundings for open system. For open system, it is not possible to measure the change of system and surrounding for an open system. So what we need, how to measure that, how to determine the spontaneity? In order to determine spontaneity, can you follow? The entropy change should be considered in terms of other state function. Instead of delta F, we can use some other state property which can be determined more conveniently and accurately. So I already pointed out, for isolated systems okay, but open system delta S cannot measure for surroundings. But in that case, instead of delta S, we can introduce another term. We can now that can be measured easily, which can be determined more conveniently. One, there are two such state functions are, we'll call it as Helmholtz free energy, usually A, and Gibbs free energy, usually G indicated. So we are now introducing two new thermodynamic functions. One is A, capital A, Helmholtz free energy, and capital G, Gibbs free energy. So we are now concentrating here, the Gibbs free energy will concentrate. That is the interesting information. Kindly follow. So free energy chain. I am now indicating nothing but delta G. Gibbs introduced by Gibbs. So we are calling it as Gibbs free energy chain. Okay. To explain spontaneity in change, Gibbs proposed a state function G. He introduced the term G. So according to him, it is given by a definition G equal to H minus Ts. What is G? We know that is, I have just now informed it is the free energy, Gibbs free energy. What is H? Enthalpy. T? Temperature. And S? Entropy. Disorder of the system. So I can now, instead of normally, it is not possible in the enthalpy or in the free energy directly, we cannot measure. Only the change in entropy, change in enthalpy, change in free energy can be measured. So I can now rewrite delta G equal to delta H minus T delta S. This is the very, very interesting equation given by Gibbs. Okay. Now from this, let me explain now. Let me explain now state spontaneity by delta G based on delta H value, T value, and delta S value as follows. So how to determine spontaneity with the help of this equation? Kindly follow. So the idea here it is, we have to determine delta G. Instead of directly measuring delta S for open system, now we are introducing by the Gibbs introduced delta G, Gibbs free energy. So Gibbs free energy is nothing but delta H. Delta H can be measured experimentally in the laboratory, and T temperature we know. So delta S now we are substituting in this case, so we can measure. So delta G can be measured easily. From that we can even delta S can be calculated. Kindly follow. Then interesting information here it is for free energy change. So now these are the three important conditions you must know, please. If delta G of the system equal to negative, kindly follow. If delta G equal to negative, the process is spontaneous. It is feasible. The reaction is feasible. So second law of thermodynamics gives very clear idea. If delta G of the system is negative, the process is spontaneous. It is feasible. Right. If delta G of the system equal to positive, the process is non-spontaneous. Very, very interesting. It is not possible. It is if the delta G is positive, the process is non-spontaneous. It is not spontaneous. Right. If delta G of the system equal to 0, the process is in equilibrium. So these are the three important information we are getting from the delta G value. So I can explain. The above fact can be explained as follows from the equation. Kindly follow. So this is the equation I am going to apply. Kindly follow. So I have already pointed out, only if delta G value equal to negative, it should be spontaneous. If it is positive, it is non-spontaneous. So whether your reaction is positive or negative, then from the delta G value, we can determine whether it is a spontaneous process or non-spontaneous process. So condition number one, kindly follow. First case, if delta H is negative, first case, and T delta S value it is positive, so right side minus into positive again minus, so delta H is also minus, so automatically more negative, so that particular reaction is spontaneous. So all exothermic reaction generally will be spontaneous. One important information. The second condition, number 2. Second condition. Suppose if delta H value positive, that is endothermic, then if T delta S value, if it is positive, so what we can think of, minus corresponding into minus will be plus. Kindly follow. That means delta H will be plus and corresponding minus, this is also plus. Kindly follow. In this case, again when will be it is minus. The resulting delta G will be minus. What condition? At a higher temperature. At a higher temperature, the temperature is very high, automatically the corresponding T delta values will be very high. So this value, very high value, this will be plus, automatically minus into plus will be, this minus T delta value will be negative, the delta H value plus, so it will be negative value, the resulting value will be negative, again it is positive. This is the interest, that is the result, this is correspondingly negative, so it is a spontaneous. The condition here it is, the delta G for endothermic reaction, if the delta G value is negative, it will be spontaneous, but only with the condition at the higher temperature, that is T delta S greater than delta H. That is the interesting information. And third condition, if delta H is equal to negative and T delta S value is also negative, automatically this is the delta G will be negative, spontaneous. How it is feasible? At a very low temperature, automatically all exothermic reactions will be spontaneous. So I can generalize now. All exothermic reactions will be generally spontaneous. Right. Coming to the next one, conditions. If delta H is positive and minus T delta, this value again, it is again negative, then you will minus into minus correspondingly positive. So that means correspondingly the total value will be positive, it is non-spontaneous. Kindly follow, this is the interesting information. So if these values are positive and these values are positive, so delta G will be positive, in that case non-spontaneous. That means in the endothermic reaction it is, and the correspondingly this value, that is delta H value should be correspondingly greater, that means, so the total value delta G value plus, it will be non-spontaneous. So let me conclude now. So the idea here it is, if the delta G value negative, spontaneous, again there are conditions, again this is for all exothermic reaction. In the case of endothermic reaction, now again it will be negative, the delta G will be resulting will be negative, only the condition is T delta S will be greater than delta H. Then another case for exothermic, again T delta S value again negative, the resulting effect again negative, spontaneous, but this is the condition that delta H will be greater than T delta S. And finally, delta H is positive, T delta is negative, the resulting value will be positive, then the process will be non-spontaneous. This is the interesting information. So, with this idea, now let me go for the last one, third law of thermodynamics. Kindly follow. Under the third law of thermodynamics, it is not given covered in this B.Sc syllabus or even some lecture. Just I will give only one statement, I will leave the lecture. What is the statement, third law? The entropy of a perfect crystalline substance is 0 at absolute 0. The entropy of a perfect crystalline substance is 0 at absolute 0. This is the interesting information. Now, the historical development of the third law of thermodynamics may be traced to the search for an explanation for the experimental observations that delta G and delta H have almost same value for many reactions. Kindly follow, even at a high temperature, delta G equal to delta H. So this is just information I want to record. I hope you have enjoyed. Thank you.